Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is voltage divider circuits. Our objective today is to take a close look at a voltage divider circuit in both the unloaded and loaded condition. Voltage dividers are common series parallel circuit configurations, and this lecture assumes you have a passing familiarity with series parallel circuit analysis. If you haven't watched the series parallel circuit analysis lecture available at the Big Bad Tech channel, or only dimly recall its contents, by all means do so now. As anyone that has ever organized or meticulously planned an event can tell you, no plan survives first contact. This is true for the biggest of battles, all the way down to a toddler's birthday party. Success, and sometimes survival, means you often have to toss that beautiful plan out the window and deal with the crumbling reality before you. The same is true for a voltage divider circuit in the unloaded and the loaded condition. If you can walk away from this lecture with a simple understanding that you cannot use any data obtained during circuit analysis of a voltage divider in the unloaded condition to solve for the same quantities while in the loaded condition, I will consider my time having not been spent in vain. Voltage dividers in the unloaded condition are totally different circuits than voltage dividers in the loaded condition and must be analyzed as such. Voltage dividers often take the form of a pure series circuit with several accessible nodes that electrical loads can be connected to in parallel. If nothing is connected to these nodes, or the switches between the nodes and the electrical loads are open, this is an unloaded voltage divider and can be analyzed using the simplest of series circuit techniques because there is but one path for current to flow. An unloaded voltage divider, as the name implies, is a perfect opportunity to apply the voltage divider rule. Here's an unloaded voltage divider with 3 resistors in series. Pause the lecture and use basic series circuit properties to solve for V1, the voltage drop across R1 only. Wait to perform the analysis of V2 and V3 and other quantities until after I've reviewed the answer for V1. The VDR set up to solve for V1 is as follows. Substituting in the necessary values, we find V1 equals roughly 7.1 volts. If you've been watching the Basic Electronics 1 DC Circuit Analysis playlist and its intended sequence, this should have been the most trivial of tasks. The only reason I had you stop here is to consider the nodal voltages with reference to ground while the voltage divider is in the unloaded condition. Let's start by assigning the nodes A, B, C, and ground. If the source makes node A 50 volts higher than ground, and V1 drops 7.1 volts from A to B, this means node B is only 50 minus 7.1, or 42.9 volts higher than ground while in the unloaded condition. If this voltage divider circuit was inside a box, and only node B and the ground reference was sticking out of the box, a voltmeter would read the same 42.9 volt differential. You might incorrectly assume any load attached between node B and ground would experience the same 42.9 volt differential as if it was a constant voltage source. But it isn't. It's a voltage divider, and there's a resistor in series between the 50 volt source and the accessible node B. This will affect output voltage, as we'll learn in a moment when we discuss loaded conditions. Continuing on, I could use the regular voltage divider rule again, or a combination of Ohm's law and Kirchhoff's voltage law to solve for V2 and V3. However, I'm going to throw a twist on the voltage divider rule to solve for one of these quantities. Here's the twist. Notice I'm only including R2 and R3 in the VDR formula, and I'm not using the source voltage. I'm using the voltage at node B with reference to ground. This is to imply that R2 and R3, those elements between node B and ground, should drop representative portions of this voltage. You can do this. This is the beauty of the VDR. As long as you're flexible, it's flexible. Substituting in the necessary values, we find V2 equals approximately 14.3 volts. Again, if this source makes node A 50 volts higher than ground, and R1 drops 7.1 volts from A to B, and R2 drops an additional 14.3 volts from B to C, this means node C is only 50 minus 7.1 minus 14.3, or 28.6 volts higher than ground while in the unloaded condition. If this voltage divider circuit was inside a box and only node C in the ground reference was sticking out of it, a voltmeter would read the same 28.6 volt differential, and you might incorrectly assume any load attached between node C and ground would experience this same 28.6 volt differential as if it was a constant voltage source. But it isn't. It's a voltage divider circuit, and there are two resistors in series between the source and the accessible node C. This will affect output voltage, as we'll learn in a moment when we discuss loaded conditions. Finally, an Ohm's law analysis of this voltage divider circuit in the unloaded condition suggests that current through any of these three resistors is approximately 14.3 milliamperes. This current internal to the voltage divider circuit is sometimes known as bleeder current. For an unloaded voltage divider circuit, source current and bleeder current are one and the same because a pure series circuit has but one path for current. If switched loads were attached to the accessible nodes B or C, and these switches were open, the voltage divider circuit is still in its unloaded condition, since no current can flow through these open switches. Switch X is between node B and load resistor Rx, a 3 kΩ resistor. Switch Y is between node C and load resistor Ry, a 2 kΩ resistor. In the open condition, switch X would experience a 49.2 volt drop between its two terminals and no current would flow through it. In the open condition, switch Y would experience a 28.6 volt drop between its two terminals and no current would flow through it. Since no current is traveling through the load resistors X or Y, these load resistors will experience no voltage drop. This all changes when one or both of these switches close, because the unloaded voltage divider has changed from a simple pure series circuit to a series parallel circuit. Absolutely none of the values obtained during unloaded conditions can be used to calculate any value during loaded conditions because these are two fundamentally different circuits and they will behave in two fundamentally different manners. Consider the radically different behavior of this same voltage divider circuit when switch Y is closed. This closed switch places the load resistor Ry in parallel with R3, and this additional path for current will decrease the resistance seen by the source, and source current will increase. Source current is now the bleeder current, that current internal to the voltage divider, and that current bound for load resistor Ry. Both R1 and R2 carry the combination of both currents. However, at node C, these two currents divide. R3 carries only the bleeder current, and Ry carries only the load current IY. Since R3 and Ry are in parallel, the closure of switch Y is in effect replacing the original series configuration of R1, R2, and R3 with a series configuration of R1, R2, and R', where R' is the parallel combination of R3 and Ry. Since R3 and Ry are both 2 kΩ resistors, R' would be equal to 1 kΩ. The loaded voltage divider circuit has fundamentally changed from its unloaded configuration. Total resistance has decreased because of the additional current carrying path. Source current will increase and voltage drop across each element and nodal voltages will be reapportioned. A loaded voltage divider circuit is a circuit fundamentally different from unloaded conditions and must be approached as such. If you feel up to the task, by all means pause the lecture and see if you can solve for the voltage drop across each component, including the switches and load resistors, the nodal voltages at node B and C with respect to ground, and the current through all elements. Here's how I solve for the desired unknowns. You may have performed different steps in a different sequence, but ultimately our answers should agree. I'll use the pure series simplification of R1, R2, and R' and start by solving for VR' using the VDR. The VDR set up to solve for VR' is as follows. Substituting in the necessary values, we find VR' to be 20 volts. R' is the parallel combination of R3 and load resistor Ry. Voltage across components hooked in parallel is the same. V3 is 20 volts, as is Vy. Additionally, it can be said that the voltage at node C with respect to ground is 20 volts. Ohm's law suggests the current through load resistor Y is equal to the voltage across load resistor Y divided by the resistance of load resistor Y. Substituting in the necessary values, we find the current through load resistor Y and switch Y is 10 milliamperes. Since R3 is equal in magnitude to RY and is experiencing the same voltage drop across it, we can be reasonably confident it too will also draw 10 milliamperes of current. An additional Ohm's law analysis supports this time-saving step. Given both R3 and RY are drawing 10 milliamperes of current each, it can be said that 10 plus 10, or 20 milliamperes of current, must have entered node C prior to being divided. This means current through R2 is 20 milliamperes, as is the current through R1, as is source current, since in this configuration there are no other paths diverting or supplying additional current. Ohm's law suggests that V2 equals I2 times R2. Substituting in the necessary values, we find V2 to be 20 volts. We can use KVL to solve for V1. A KVL analysis of the pure series simplification suggests E equals V1 plus V2 plus VR prime. Substituting in the given value of E and the calculated value of V2 and VR prime, and solving for V1, we find V1 to be 10 volts in this configuration. Our KVL analysis also suggests either E minus V1 or V2 plus VR prime equals the voltage at node B with respect to ground. Therefore, node B is 40 volts higher than ground. In this case, the bleeder current, that current internal to the voltage divider, is 10 milliamperes, and the additional 10 milliamperes of current bound for load resistor Y is coming along for the ride through R1 and R2 before it takes a turn at node C to its intended destination. The current through switch Y is 10 milliamperes, and since we're assuming switch Y is an ideal closed switch with no internal resistance, there will be no voltage drop across its two terminals. Open switch X experiences no current through it. Since node B is 40 volts higher than ground, the voltage across switch X's two terminals is 40 volts. Since no current is flowing through load resistor Rx, there will be no voltage drop across it. Compare and contrast the values we obtained during unloaded conditions and that when switch Y is closed. Not one of the values we obtained are identical, with the exception of the current through the open switch X and the voltage drop across the unconnected load resistor Rx. The only reason these values are the same is because in both circumstances, load resistor Rx is totally disconnected from the circuit and does not influence it in any way, shape, or form. The larger take-home point is this: the connection of load resistor Ry changed everything, including points above stream of it. The moment contact is made, even the best of plans must change. Consider now what happens when we close switch X. This is again a completely different circuit than our previous unloaded analysis and when the voltage divider circuit was loaded only by the load resistor Ry. In this case, bleeder current still travels through R1, R2, and R3. The current bound for load resistor Rx travels through R1 before getting off at node B. The current bound for load resistor Ry travels through both R1 and R2 before getting off at node C. In this case, source current increased because the addition of yet another path in parallel decreased total resistance seen by the source. As can be expected, everything will change. Load resistor Ry is still in parallel with R3 at node C. A simplification I'll call R prime, with a value of 1 kiloohm. R prime is in series with R2. These can be taken together as another imaginary resistor I'll call R double prime, with a value of 1 kiloohm plus 1 kiloohm, or 2 kiloohm. Note by combining these two resistors in series, we've effectively lost access to node C. However, we can always return to this point if we keep track of any simplifications we've made in the process of solving for our desired quantities. R double prime is in parallel with a 3 kiloohm load resistor Rx at node B. These two can be combined in parallel to yield another imaginary resistor I'll call R triple prime. Since R double prime is a 2 kilo ohm resistor and Rx is a 3 kilo ohm resistor, the parallel combination of these two means R triple prime is a 1.2 kilo ohm resistor. R triple prime is in series with a 500 ohm R1. We can now apply the voltage divider rule to solve for VR triple prime. The VDR set up to solve for VR triple prime is as follows. Substituting the necessary values, we find VR triple prime to be approximately 35.3 volts. Since R triple prime is the parallel combination of R double prime and load resistor Rx, we can say that voltage across components hooked in parallel is the same. VR double prime is 35.3 volts, as is the voltage across load resistor Rx. This also means node B is 35.3 volts above ground. Given V1 is in series with R triple prime, a Kvl analysis of this loop suggests that V1 equals 50 minus 35.3 volts, or the remaining 14.7 volts. Ohm's law suggests that I1 equals V1 divided by R1. Substituting the necessary values, we find the current through R1 is 29.4 milliamperes. This means source current is 29.4 milliamperes. This is the current that enters node B, the parallel combination of R double prime and load resistor Rx. Ohm's law suggests that Ix, the current through load resistor Rx, is equal to the voltage across it divided by its resistance. Substituting in the necessary values, we find Ix, the current through load resistor Rx, is approximately 11.8 milliamperes. With our previous understanding that approximately 29.4 milliamperes of current entered node B and 11.8 milliamperes of it went through load resistor Rx, it can be said that the remaining 17.6 milliamperes traveled through R double prime, where R double prime is the series combination of R2 and R single prime. Returning to the previous level of simplification, this suggests that I2 should equal 17.6 milliamperes. Ohm's law suggests that V2 equals I2 times R2. Substituting the necessary values, we find V2 should equal approximately 17.6 volts. If the source makes node A 50 volts higher than ground, and R1 drops 14.7 volts from A to B, and R2 drops 17.6 volts from B to C, it stands to conjecture the voltage at node C with reference to ground is the remaining approximately 17.7 volts. This means V3 is also approximately 17.7 volts, and Vy is also 17.7 volts, since they are in parallel with each other. If at node C, 17.6 milliamperes of current enters the parallel combination of R3 and Ry, we can use either Ohm's law or the current divider rule to determine how the 17.6 milliamperes of current divides between R3 and load resistor Ry. However, we're aware that both R3 and Ry are resistors of the same magnitude of 2 kiloohms, with the same voltage drop across them. Current entering node C should split equally between them. I3 equals half of 17.6 milliamperes, or 8.8 milliamperes, as does Iy. Since we're assuming switch X is an ideal closed switch with no internal resistance, there will be no voltage drop across its two terminals. The same thing could be said about switch Y. Assuming it's an ideal closed switch with no internal resistance, there will be no voltage drop across its two terminals. Again, notice the values we obtained when both switch X and switch Y are closed are totally different than when only switch Y was closed or during unloaded conditions. The closure of both switch X and switch Y makes this a totally different circuit, and it must be analyzed as such. The moment contact is made, even the best of plans must change. Consider yet another permutation of this same voltage divider circuit. What if switch X was to remain closed and switch Y were to open, effectively removing load resistor Ry from consideration? This is another circuit entirely and must be treated as such. This is why I love voltage divider circuits so much. There are numerous possibilities, and each configuration brings with it a new chance to put our series parallel circuit analysis skills to the test. In this configuration, R2 and R3 can be combined in series with one another into something I'll call R prime. Since R2 is a 1 kΩ resistor and R3 is a 2 kΩ resistor, R single prime would be 3 kΩ. R single prime is in parallel with Rx, also a 3 kΩ resistor. These two resistors could be combined in parallel into something I'll call R double prime. Since R single prime and Rx are both 3 kΩ resistors, R double prime will have a value of 1.5 kΩ. The VDR set up to solve for VR double prime is as follows. Substituting in the necessary values, we find VR double prime equal to 37.5 volts. Since R double prime is a parallel combination of R single prime and Rx, this means Vx, the voltage across load resistor Rx, is also 37.5 volts. Additionally, this means node B is 37.5 volts higher than ground. The Kvl analysis of the simplified pure series circuit suggests E equals V1 plus VR double prime. Substituting in the given value of E and the calculated value of VR double prime, and solving for V1, we find V1 equals 12.5 volts. Ohm's law suggests V1 divided by R1 equals I1. Substituting in the necessary values, we find I1 equals 25 milliamperes. Given I1 is the combination of bleeder current, the current internal to the original voltage divider, and current bound for load resistor Rx, we can say source current is also 25 milliamperes, and use either Ohm's law or the current divider rule to determine how the 25 milliamperes of current entering node B divides between R prime and load resistor Rx. However, we're aware that both our imaginary resistor R prime and load resistor Rx are resistors of the same magnitude of 3 kΩ with the same voltage drop across them. Current entering node B should split equally between them. IR prime equals half of 25 milliamperes, or 12.5 milliamperes, as does Ix. Given R prime is the series combination of R2 and R3, it can be said that the current through these two resistors should also be equal to 12.5 milliamperes because they are in series with one another. I2 equals 12.5 milliamperes, as does I3. Ohm's law, Kirchhoff's voltage law, or the VDR suggests V2 equals 12.5 volts and V3 equals the remaining 25 volts. Therefore, node C is 25 volts above ground. No current will flow through open switch Y, and no voltage will be dropped across load resistor RY. Given node C is 25 volts higher than ground, open switch Y will experience a 25 volt drop across its two terminals. Ideal closed switch X should exhibit no voltage drop across its two terminals. Again, this circuit analysis yields radically different values than any of our previous analyses because this is a radically different circuit than our previous renditions and must be approached as such. Voltage divider circuits and their numerous configurations present one with numerous opportunities to practice series parallel circuit analysis skills. This single circuit presented us with 4 different opportunities to employ our skills. Once in the unloaded condition, when neither switch X nor switch Y was closed. Another when it was loaded by RY only. Another when it was loaded by both RX and RY. And finally another when it was loaded by RX only. Each different combination of switch positions presented us with different current paths and resultant voltage drops. Every situation was different and necessitated a completely new analysis because they were completely different circuits. Notice at no time did I ever have to resort to reducing this circuit to a single total resistance and return through a tangled mess of simplifications to solve for the desired quantities. At all times I used basic series and basic parallel properties and repeatedly made use of Kirchhoff's voltage law and Kirchhoff's current law to quickly and directly solve for the desired quantities without any hard-breaking labor. Visualize circuits at the nodal level from the perspective of flowing current. If there is no choice of paths, those elements in the same paths are in series with one another, and current through them must be the same. If there is a choice in paths, those paths are in parallel with one another, and voltage across them must be the same. In this spirit, here's not one, but rather 8 different opportunities to put your skills to the test. Here's a voltage divider circuit consisting of a 12-volt source and 3 resistors, R1 at 200 ohms, R2 at 400 ohms, and R3 at 600 ohms, with 3 switches and 3 loads. Rx is a 1.2 kilo ohm resistor, Ry is 1.8 kilo ohm resistor, and Rz is a 2.4 kilo ohm resistor. Pause the lecture and solve for the voltage drop across each component, the current through each component, the source current, and the bleeder current. Recall, the bleeder current is the current internal to the voltage divider, in 8 different switch positions as indicated in the table in the upper right-hand corner. You may be bummed out about the number of repetitions. However, a quick Kirchhoff's current law analysis of one of the switches in the electrical load will allow you to make a powerful and time-saving deduction about that load resistor's effect on the remaining circuit. I'll not go into details about the calculations of the required values, since the methods employed can be numerous. I will, however, dispense general advice that may serve to guide you through resolution of each problem. Don't wait for me to give you the answers. If a hint frees you from a sticky spot, by all means pause the lecture and see if you can take it from here. Our first scenario is one in which the voltage divider is unloaded and all switches are open. The simplest of series circuit analysis techniques will suffice. All current travels through R1, R2, and R3, and all voltage will be proportionally distributed between these resistors. No current travels through Rx, Ry, or Rz, and no voltage will be dropped across them. The voltage drop across each open switch will be the nodal voltage with respect to the ground reference. When switch Z is closed, Rz is placed in parallel with R3 and R3 only. Source current will travel through R1, R2, and only at node C will bleeder current and current bound for load resistor Rz part ways. Since R3 is in parallel with Rz, the voltage drop across these two components will be the same. Supply voltage E will be proportionally distributed between R1, R2, and the parallel combination of R3 and Rz, R'. No current travels through Rx or Ry, and no voltage will be dropped across them. The voltage drop across each open switch will be the nodal voltage with respect to the ground reference. When switch X is open and switch Y is closed, Ry is placed in parallel with something I'll call R', the series combination of R2 and R3. Source current will travel through R1, and at node B, bleeder current and current bound for load resistor Ry part ways. Since R' is in parallel with Ry, the voltage drop across these two components will be the same. Internal to R', since R2 is in series with R3, R2 and R3 should have the same current. Supply voltage E will be proportionally distributed between R1 and R', the parallel combination of R' and Ry. No current travels through Rx or Rz, and no voltage will be dropped across them. The voltage drop across each open switch will be the nodal voltage with respect to the ground reference. When both switch Z and switch Y are closed, Rz is placed in parallel with R3, something I'll call R'. R' is in series with R2, something I'll call R'. Source current will travel through R1, and at node B, current bound for load resistor Ry parts ways with that current bound for R'. At node C, bleeder current and current bound for load resistor Rz part ways. Since R' is in parallel with Ry, the voltage drop across these two paths will be the same. Since R3 is in parallel with Rz, the voltage drop across these two components will be the same. No current will travel through Rx, and no voltage will be dropped across it. Supply voltage E will be proportionally distributed between V1 and Vr', where R'' is the parallel combination of Ry and R'. When switch X is closed and all other switches open, the voltage divider could care less what Rx is doing. Rx has been placed perfectly in parallel with a series combination of R1, R2, and R3. This analysis will be nearly identical to the unloaded condition, with the single exception that Rx now draws current and experiences a voltage drop, and source current has increased. This can be extrapolated into the remaining scenarios in which switch X is closed, such as when switch X is closed, switch Y is open, and switch Z is closed. Switch X is closed, switch Y is closed, and switch Z is open. And finally when all three switches are closed. Since Rx is placed perfectly in parallel with the voltage divider, it does not affect voltage division internal to the voltage divider. Only those load resistors internal to the voltage divider affect it with their presence. If you've done the analysis of this voltage divider correctly, you should expect to observe the following values for the following conditions. In the unloaded condition, one would expect to observe the following values. Our second scenario, in which only switch Z is closed, one would expect to observe the following values. For our third scenario, in which only switch Y is closed, one would expect to observe the following values. In the fourth scenario, when both switch Y and Z are closed, one would expect to observe the following values. In our fifth scenario, in which only switch X is closed, it's almost like it's a repeat of the unloaded voltage divider, the minor exception that source current has increased because load resistor Rx is now drawing current. In our sixth scenario, when both switch X and switch Z are closed, we find something very similar to just when switch Z was closed, the one exception being the load resistor Rx now draws current, and source current will increase. Our seventh scenario, in which both switch X and switch Y are closed, is very similar to the scenario in which just switch Y is closed, the one exception being that load resistor Rx draws current and experiences a voltage drop, and source current increases. Our final scenario, in which all three switches are closed, is very similar to our previous analysis of just when Y and Z were closed. The only exception is that load resistor Rx draws current and source current will increase. Please take your time to revisit any calculations that may be in error and pause to consider the general guidance I issued before giving you these answers. Visualize circuits at the nodal level and from the perspective of flowing current. Elements within the same path must have the same current. Paths in parallel must have the same voltage drop across them. In closing, I leave you with this voltage divider circuit to tackle on your own as an assessment exercise. I'll post the answers to this problem in the information section associated with this lecture. Don't peek. Try this one by yourself. If you can arrive at the same answers, you have met the standards for success for this task and can feel free to move on to the next section. If not, I suggest you revisit this lecture and correct any misconceptions you may have before continuing. We have a 40-volt source supplying a combination of R1, 400 ohms, R2, 600 ohms, where switch X is switching the series combination of RX1, a 1.2 kilo ohm resistor, and RX2, another 1.2 kilo ohm resistor. Switch Y is switching load resistor RY, a 2 kilo ohm resistor. Solve for voltage across each component, including switches, and the current through each component, including source current and bleeder current, for 4 different conditions. One when both switches are open, one when switch Y is open and switch X closed, another when switch Y is closed and switch X is open, and finally when both switches are closed. You may find circumstances in which different switch positions yield the same answer for very fundamental reasons. In conclusion, this lecture took a look at a common series parallel circuit called a voltage divider in both the unloaded and loaded condition. We learned that values obtained during circuit analysis of the unloaded condition cannot be used to calculate values during the loaded condition because the unloaded and loaded condition present radically different circuits and must be approached as such. Remember to review these concepts and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.